let's have a look at the correspondence problem. How are we going to find the same point? Which are these strategies? One of the methods that is widely used is this shift method that I told you. Okay, we're not going to see shift in this part of the class, but we will see it later on. All right, we're going to see what are the basic before shift. How were people finding out if this point is this other point in the other image? Okay. So the matching methods that we're going to see, matching in the sense that they are able to match this point, given this point in this image, what is its corresponding point, what is its match in the other image. We're going to see these four methods: sum of square differences, sum of absolute differences, cross correlation, and normalized cross correlation. Okay? So how does this work? Imagine that I start with interest points or corners. Imagine that I have applied Harris. Okay? And this is image 1, this is image 2, and what I have done is I found this point in image 1, and I found this point in image 2. And I want to know, and in image 2 I found all the corners. Okay? And what I'm going to do is, okay, out of the 10 corners that I detected in image 2, which one corresponds to this corner of image 1? And the way to do it, in this case, is the sum of square differences. I'm going to just draw. Okay, I'm going to draw this and this in the next slide. So this is the first patch that I have. This is the second patch. Wow, this is the second patch. Looks very bad now. So this is the second patch. Okay, you understand that these two windows are exactly the same size, and they are squares. Okay. So the sum of square differences is just a matter of taking this gray value here minus this gray value here to the square, plus this gray value here minus this gray value here to the square, plus this minus this, and so on. And you see what I get is this equation here. Is a double sum for x and y, and I have here the patch, the pixels. I and j are my indices here to move around this window, and I and j allow me to move around this window. Okay, and this is what I do. I just take the gray values, I subtract them, and I apply the square.
Why x1 plus I and x2? Why you are moving from x2 and from x1?
Because in this case they are, so why is this different from this? It's because is this pixel and this pixel the two corners that I want to compare? You see, in image 1, the coordinates of this point are x1 and y1. And in image 2, the coordinates are of the center pixel are x2 minus y2. Okay, remember that I will do this for this patch, but then I will do this for this patch. And I will compare this to this in the same way. Given this point in image 1, and given 10 points, which are 10 corners in image 2, I want to find out which is the correspondence of this point in the second image. And the way to do it is, I am going to do 10 times this operation. 10 times. The first time I'm going to start with this point. So x2, y2 is going to be this coordinate here. And I get sum of square differences. This sum of square difference is going to give me a value. Then I do it for this pixel. So this x2 and y2 are going to be this coordinate here. And now I'm comparing this patch to this patch. And I get another sum of square differences. And the sum of square differences for this second one is bigger. Do you think it's the right match? Or is worse than the first one?
Worse.
It's worse. Because the smaller the sum of square differences, the closer the two patches are. Okay? Once I do this 10 times, I say, okay, this is the best, because it's given the smaller sum of square differences.
This is the point.
And, no, wait. And then I'm going to say, is this larger than a given threshold? Or it's smaller than this threshold? I'm not going to accept the closest one. I'm going to accept the closest one, so the one that gives the smaller sum of square differences, if it's below the threshold that I set. I said, okay, my threshold is going to be 2,000 or 200. So if it's under 200, I accept it. If it's over 200, the smaller one is over 200, I'm going to say, maybe at this point, I didn't detect it in the other image. So maybe it doesn't exist. All right? What is the problem with this? The first problem is that, remember that situation where I told you that I have different exposures, and this is 100, and this is 50, and here this is 200, and the patch is 100? Is this going to work when I get the right match? No, because I'm using the intensities directly. So I'm not able to compensate for these differences in the intensity of the images. So this is not going to work. Is this going to work if I have a rotation in the image? It's not going to work. Is it going to work if I have a scale change in the image? It's not going to work either. Okay? Maybe in some situations there's a patch that looks similar, but mathematically it's not the same. It's not going to work. Okay? So it's not invariant to rotation, it's not invariant to changes in intensity, it's not invariant to changes in scale. I could do the same as the sum of square differences, taking the absolute value. Instead of squaring them for preventing the two, a positive and a negative component of the summation to cancel, so I can take the absolute values, and it's the same idea. So it has the same problems. Thresholds are going to be different, but it's the same problem. Okay. How about normalized cross correlation? So the idea of normalized cross correlation is, now let's consider only this patch and this patch again, like before. What I'm going to do is I take the first pixel in the first patch, which is this thing here, and instead of just multiplying it, in this case for correlation I multiply, by this intensity in this other pixel, what I'm going to do is first I'm going to subtract the average intensity of this window. So I take the gray value of the first pixel minus the average gray value of the full image times, I'm going to multiply these, times the gray value of this pixel minus the average gray value of the second window. Why am I doing this? I'm trying to compensate for differences in lighting. So the normalized cross correlation is taking into account this effect, in which I said this is 100 and this is 50 and this is 200 because there's twice much light, and this is 100. The correlation is going to work perfectly. Okay? Even if it's not just, even if it's an affine transformation, it's going to have robustness against this. Okay, and then I divide by the area of the window, n plus 1 square. This is the size of my window, times the product of variances. What's the variance in the first patch? What's the variance in the second patch? So this is the normalized cross correlation is taking into account these differences in intensities. Okay. So if I have an affine change in intensity, this is going to perform better than the sum of absolute differences or the sum of square differences. However, is it going to work if I have a rotation? No. I mean, if you have rotations larger than, I would say 10 degrees is very optimistic already, but 5 degrees are still okay. 10 degrees, you're quite in a trouble already. Is it going to work if I have a change in scale? It's not going to work because I'm looking at the patch and I'm looking at a different patch if I have a change in scale. So if the camera gets closer and I get another image, it's not going to work. Normally, when you do this, you're not so sure about the location of your corner. And normally what you do is you open a search window around the corner that you detected, the interest point that you detected. And then you don't apply the correlation just here. You don't take this here and compare this window to this window. Normally what you do is you open a search window, and then I apply this in this position, and in the next position, and in the next position, and I run several correlations. And then I take the maximum of these correlations. And I say, oh, if the maximum was found here, then I say that this patch is the correspondence to this patch here. Normally you define the search window around the corners that you detected in the second image. So you do Harris here, imagine you find 10 points, 10 corners. 10 is a dramatically low number, on the other hand. So in reality, you want to find more. But imagine you have 10 here, and you have 10 here. And then for every one that you have here, you open a search window, and you do several correlations. Okay? And then you end up saying, okay, the good correspondence is... This search window was used normally for motion estimation many years ago, in which you know that you have a video camera, and imagine that you're acquiring 25 images per second. This means that from one image to the next image, you only have 40 milliseconds. So in 40 milliseconds means that if this point was here in the previous image, in the next image is not going to be far from this position. And then you can predict where this point should be and open a search window there. This means that you only detect corners in one image, and in the second image you just track those points. You don't need to detect corners again. But you could, if your frame rate is high enough, then you can look for a correspondence in a close enough area. If you do this, normally the scale is not going to change too much in 40 milliseconds, and the rotation is not going to change too much in 40 milliseconds. So everything fits. If you have 10 corners here and 10 corners here, it's quite likely that out of these 10 corners, maybe only 7 of them were detected here, or 6. So, and if something goes wrong in finding the same corners, you might not be able to estimate motion. Normally, when you do this, you do it with 200, 300, 400 points per image. And then you have an explosion of computational cost if you want to try everything with everything. This is why you want to use these search window strategies, depending on what you're doing. Okay? But these were the methods that existed before 2004, where David Lowe presented his SIFT paper. So now, everybody, most of the people, are using SIFT. And SIFT is invariant to scale, and is invariant to rotation, and is robust to affine transformations. So, it has changed the way people look at the correspondence problem. But still, it doesn't work perfectly, because solving the correspondence problem is a very difficult task. It's not easy. Okay. So let's continue. This is just an example for you to see. Imagine that I look at 2 frames, 2 consecutive frames. This is a video frame. This is 25 images per second, so there's 40 milliseconds between this image and the next image. And then imagine that I just take this as a patch. This is just to show you how things could work. You have this player here. I define this search window. And now I apply this window. I correlate this rectangular window. I correlate it with all the points in the next image, 40 milliseconds later. Of course, this player didn't change position or didn't change much in the shape from one image to the next image in 40 milliseconds. And then if you do this correlation, you see, in this case it's not a correlation, is the sum of square differences. You see that you have big change all around, but you have a black dot here, or a black patch here. Because this is the same as with Harris. You don't only get a low value for the sum of square differences exactly at the position where this patch was taken, but also the neighboring positions also provide low values. Okay, but the peak, the lowest, the minimum, the local minimum is going to be where you're going to say, okay, this is my, so this point corresponds to this position in this image. But in this case, this could be used, for instance, to do a tracking of a given player if my frame rate is high enough. Okay, it's just, see different applications of what we have seen so far.